today, what I'm going to talk about is the nature of dark energy, okay? But before that, as Enrico has introduced me, I'm Mahdi Najafi. I'm currently a PhD student at Sapienza. And I mainly worked on cosmology, but the talk that I'm going to talk about today is the work that I've done on my previous university at Khaja Nasir, under the supervision of Eleonora Di Valentino and Dr. Firuzjai, which I had to shout out their name and thank them before I start. So today, what I'm going to talk about is nature of dark energy and what does the precision cosmology says about the nature of dark energy. Okay, precisely the CMB, BAO, and supernova observation. Okay, so as we know in cosmology, depending on who you are asking, about 95% of the universe is the mystery, that are the mystery of dark energy and dark matter. So today, the structure of my talk will be that I'm going to have a broad introduction to cosmology, homogeneous universe. Then I'm going to talk about, to add inhomogeneity to universe, to study the structure formation in the universe. Then I'm going to explain how do we study the universe that we are observing. Then I'm going to talk about the nature of dark energy, precisely according to CMB datasets. Then I'm going to briefly, very briefly, talk about what DESI 2024 measurements of BO says about the nature of dark energy. And as you know, it preferred a dynamical nature for dark energy, but we investigated that, is it just a fluke? Is it just based on the model that they choose? Or no, the dynamical nature is intrinsic in the data set of DESI. And at the end, I'm going to conclude my talk and talk about the future of the precise, the era of precision cosmology. As we know, in 1915, Albert Einstein published his paper of general relativity, which simply was a bridge between the geometry of the universe and the matter component of the universe. And equation 1 is completely describing his idea. Okay. Then Hubble discovered that by using Cepheids and measuring their distance and their velocity and redshift, he noticed that actually the universe is expanding. And equation 2 is actually embodied that expansion, which is just a relation between the physical distance and the co-moving distance. And these two can be related to each other by a coefficient called scale factor, which is time dependent. And this equation is very simple because if you consider any coordinate system, you could have a 0 point and a 1 point, okay? If your universe in this coordinate system is expanding, your zeros will always be 0 and your 1 will always be 1, okay? But the distance could be a stretch because the universe is expanding. This is the idea of the expansion universe. Now, how do you describe such universe, okay? First, in cosmology, we have the cosmological principle, which in a sense says that if it doesn't matter where you look at the universe, everything looks the same. Hence, homogeneity and isotropy. Now, in order to describe such universe, we need to know our geometry of the universe and the matter component. The geometry of the universe can be described by the line element in Friedmann-Lumet Robertson-Walker metric, which in a flat expanding universe is equation 3. And for the matter component, we can use perfect fluid, which is equation 4. Now, we know how our geometry is behaving, what are our matter components. What are the equations that governs this expansion of the universe? Now, these equations are Friedmann equations, which are equation 5 and equation 6. particularly equation 5 is very important because it is it has a ratio of time derivative of a scale factor over a scale factor, which we all know it as the Hubble parameter, and its value at current current time is h0, or Hubble constant at the present time. Now, we can use conservation of energy momentum in order to see how each component of the universe is evolving. And to do so, we know that in cosmology, we usually use barotropic equation of states, which is simply the ratio of pressure over density of each component. And for radiation and pressureless matter, the components evolve as equation 9, which you can see. And for radiation, the density goes on with the power with respect to 8 to the power of -4, and for pressureless matter, it's -3. Now, if we want to, simply see what is the equation that, now that we know everything, how can we simply describe the expansion of the universe? We can introduce a density parameter, which is omega I, and rewrite the first Friedmann equation as equation 10. Now, the real question is, how does dark energy evolve with time? Is it dynamical or is it constant? If we consider dark energy equation of a state to be -1, we are dealing with the lambda CDM model. Now, if we look around us, we will see that there are actually structures in the universe. And in order to study these structures, we need to have some inhomogeneity seeds in the universe. So we will introduce perturbations to the metric, and then we will study the universe. We will study this perturbation at linear level. Now, how do we add this perturbation to our equations? First, we will perturb our metric, which we can use a synchronous gauge to do so, which will change our description of metric to equation 11. And here eta is a conformal time, which is simply your physical time over your scale factor. And by working in Fourier space, in order to study this perturbation by wave number, we will define density perturbation and velocity divergence of this perturbation, which will lead to the equation 12 and equation 13, which are governing our perturbations, how the dynamics of our perturbations, how they are evolving with time in the history of the universe. Now that we know the universe, the studies and the observations has shown that lambda CDM can actually very well describe the universe with only 6 free parameters, okay? Which, as you can see, the famous plots of the Planck collaboration results of 2018, you can see our prediction very well matched with the data that we are studying. Now, here we in what we have done, we have studied the universe. We studied the dynamical dark energy scenarios by focusing on 3 major data sets, which were CMB, Baryon Acoustic Oscillations measurements, and supernova measurements. For CMB, we have used Planck, ACT, SPT, and in order to have a complete multiples, we have combined ACT and WMAP and SPT and WMAP together to have the full picture. And for Baryon Acoustic Oscillation, we have used EBOS and DESI. And for supernova type 1A, we have used Pantheon and the newer version, Pantheon Plus. Now, as we might know or might not know, the universe, as I said, is going to the expansion phase, is expanding, okay? But it is an accelerating expansion, okay? What could be the reason of this acceleration? Now, the most famous one is to consider it vacuum dark, to be a vacuum energy, or in the words of cosmology, the lambda term, which is a constant energy of empty space, and in GR could be the repulsive gravity of lambda. Or the nature of dark energy could be dynamical. Or the third option could be that maybe it is not even that complicated. Maybe if we change change how we are describing the geometry of the universe, which we all know as modified gravity, maybe we can have some new explanation for the universe or for the measurements that we have other than GR. Now, as I've said, the CMB is very well describing the universe with with our prediction. So prediction and data are completely aligned. What are the problems? Well, one of the most famous one is the cosmological constant problem, which is the 10 to the power of 120 order of magnitude difference between prediction and the observation. The other one is the famous H0 tension, which most of us here are very interested in, which is the discrepancy between the direct measurement and indirect measurements of H0, which is about 4.8 sigma from the last time I've checked. And also we have a S8 tension, which is again a discrepancy between the Planck and the S8 measurements, like kids and observations that are measuring S8, which is about 2.9 sigma, 2.6, 2.7, depends on what paper you're studying. Also, we have the why now question, which is like why the values of lambda and omega lambda and dark matter and everything that we are seeing is exactly like this. They are at the same order of magnitude, which is a bit, is it coincidence? What is it? How can we deal with it? Now, as we know, the source of this tension could be systematics, or there could be some new physics behind it. So there is a lot of studies that goes through each experiment. So I won't talk about systematics, and I think they are very well studied. People can refer to the original paper and see if they can see anything questionable. But as some studied and some model has suggested, new physics could very well remove this discrepancy between what we are seeing and what we are predicting and what is actually going on with the universe. So alternative models are actually very, very needed. One of the prominent alternatives is dynamical dark energy, which is the most famous one is the CPL, Chevalier-Polarski-Linder parameterization, which is equation 14, and Z here represents redshift, and its relation with the scale factor is equation 15. But as you can see, it will add 2 extra free parameters to already 6 parameter space that we had. Now, adding 2 extra free parameters, especially dark energy parameters, will mess up our measurements. For example, when these 2 parameters are added, the measurements of H0 is completely gone, and it only put lower limit on H0. So in order to deal with it, we need complementary data set. The other solution that we can use is to use another model, which can maybe add correction to the CPL model. And the model that we have studied is generalized exponential format for the dark energy equation of state, which is equation 16. Now, it has 2 benefits. One is that its first order of expansion returns CPL, and 2, the second and third order terms, which I call them CPL-A and CPL-B, add correction to CPL without adding any extra parameters. So it's very convenient. But what does the data set, what does the CMB sets in particular? For CMB, for the first work, we have used Planck 2018 and ACT plus WMAP, which I refer to them as ATW and SPT plus W map, which I refer to them as STW. These two are ground-based, so they're different with Planck. And also, we want to see, does it actually help to study the nature of dark energy or not? In a sense, does it give us any measurement on W0 and WA? Okay, so the methodology that we have used. First, we have to see how these how density parameter in this scenario is evolving. In our case, the equation that was governing our the dynamics of the universe was equation 19, and the data set that I've used, you can see it here. It was Planck, ACT, SPT, and all the stuff that I said. But the BAO dataset that we have used was EBOS, STSS, and Pantheon, not Pantheon Plus. We have used CAM to do our numerical collection calculation, and also in order to explore our posterior distribution, we have used Cobaya. In order to see if our model is good or not, we have used chi-squared and log Bayesian evidence, which if I said in my talk Bayesian evidence, I'm referring to this log Bayesian evidence, which we are working with the revised Jeffrey scale. And the prior that we have used is here. You can see it here. But please keep in mind that ACT and SPT doesn't measure tau. So if you want to study them, you have to consider a Gaussian distribution for them and not the flat one that are in the table. Okay. Now, for the exponential parameterization, what we have seen. We've seen that some parameters got 1 or 2 sigma shifted. The amount of omega matter for Planck was very low because, as I've said, H0 is very high and very unconstrained. But for ground base, we were able to have very large error bar with H0, but it's still a measurements. So higher, therefore, we got some higher values for omega matter. The nature of W0 was very phantom for Planck, but for ground base, it was quintessence like. And all of them were consistent with the cosmological constant. Now, the term that controls the dynamical nature of dark energy was WA, which we are very interested in. Planck was able to put only upper limit. ATW didn't consider WA to be 0 at 68% of confidence level, and SCW was considering it to be 0. So the dynamical nature was very favored for ATW. And as we could have guessed, when complementary data sets are added, our measurement got better, but I won't go into the detail because I think I don't have a lot of time left. But for the chi-square, we saw a mild improvement in chi-square, which was, again, predictable because we had 2 extra degree of freedom, but it wasn't favored by the Bayesian evidence. By going to CPL, our main point, we saw that, as I've said, for some of our measurement were not very well constrained, especially for WA, which Planck and ATW put only upper limit, but SCW still was able to give us some more concrete measurements. And just like before, when BAO were added and supernovae were added, our measurements got better. And the goodness of it were the same for all cases, even for CPLA and CPLB. But here's the difference. In CPLA and CPLB, we actually were able to get better measurement on some cosmological parameter. In particular, WA parameter, as you can see on the right figure and in the middle figure, which, as you can see, as we go to the higher order of correction, we are starting to see a more Gaussian shape on our posterior distribution. We are starting to seeing the peaks. It means that we are at least getting some measurement at 1 sigma level. It has another benefits, which when we added complementary data sets, the measurements were better and very well constrained with tighter error bars. So going to higher order of correction actually worked in this case. And here is a summary of everything that I've said, which the most important part is the nature of dark energy, which, as you can see in the middle panel, some models at least more than one sigma level doesn't include WA to be equal to 0, which means that they are favoring dynamical nature for dark energy. Also for H0, as you can see, if we use CMB alone data sets, the error bars are very large, but when the complementary data sets are added, they tend more towards the lower values, the Planck values. Okay, but I think we all know that DESI measurements considered a dynamical nature for dark energy. And DESI used CPL model. So is it coincidence? Is it just CPL model that favors dynamical nature for dark energy, or no? The data sets actually support this. And if we use different models of dark energy equation of states, the dynamical nature is still there. This is what we did in the second work. Now, this is the plots and the values that DESI has reported, and we can see that when DESI is combined with CMB and supernova, it has 2.5 sigma up to 3.9 sigma discrepancy with the value of the lambda CDM. So it is clearly hinting towards a dynamical nature for dark energy. The models that we have used were exponential, JBP model, logarithmic model, and BA model. And in general, we use alternative model parameterization to CPL to see if there is, we can see the discrepancy with lambda CDM or not. Now here, the difference is that for the CMB, for the BAO measurement, we use DESI, and for supernova measurement, we use the updated version, which was Pantheon Plus. And we saw that actually the dynamical nature is very intrinsic, and it doesn't matter, it doesn't depend on the parameterization that you are using. When Planck and DESI dataset were used, the delta chi-square was the first line that you can see, but when supernovae data were added, we saw enhancement to the values of delta chi-square that we were seeing, which means better fit to the model. And from every model that we have studied, we noticed that CPL is never the best fitting model. And using all three different data sets, BA has most improvements in delta chi-square, and JBP had the least. And in order to see if we can relate this to a physics, we also study how equation of a state for each model is evolving with time, which, as you can see for JBP model, it has two phantom crossing, two times it crosses the -1. So it's a bit complicated, numerically, maybe, should I say. And for BA, as you can see, if we move toward the higher Z, lower Z, no, sorry, higher again, it is facing a plateau. Now, to conclude and discuss about the future, hints for dynamical dark energy is actually strongly supported with the current observation, whether it's CMB. Now, for CMB, it's a bit weaker, but if we want to talk about DESI and its combination with CMB and supernova, it is very strongly supported. The improvement in observation, okay, we can see improvement in our measurements by improving the observation. So, for future more precise observation, we could even have better results. There are a lot of unexplored modified gravity and phenomenological model that can be studied, and lots of unexplored effect of nature of dark energy, such as ISW effect and structure formation and power spectrum, and all the good stuff that our cosmologists can use to study the universe are still unexplored with the new datasets. And that was my talk. These are the papers that I have worked, and I have to thank William Giare, Supriya Pan, Eleonora Di Valentino, Dr. Firuzjai, and Masouma Rehani, and everyone who has helped me with the paper and the work and the presentation. Thank you all for listening.